All right. Hi everyone, I'm Stephen Downs. Welcome once again to Ethics, Analytics, and the Duty of Care. Today we're going to look at applications of analytics, and ignore the date on the slide. I meant to do it yesterday, but I ran out of time, so we're doing it today. We'll do more videos Wednesday and Thursday, and then wrap up Friday with the discussion. So, applications of analytics. Oh, that's kind of small. Let's make that bigger. That's much better. That's the topic that we're covering for this current section in the course. This is Module 2, and so this slide is intended to, or this presentation is intended to provide an overview of what we're looking at for Module 2. I'm going to begin by looking at why people are so interested in artificial intelligence and analytics, especially for learning and learning-related purposes. Here's an example from Kay, Korn, and Oppenheim talking about responding to economic and competitive pressures, providing agility of analysis, good practices, intelligent personalized services, and visualization of patterns and trends in large-scale data. Now, these were the applications that people were thinking of in 2012. I think that we'll find that there are many more things that we now know that people can do with analytics and artificial intelligence, and as a result, there are correspondingly wider motivations. But I think the point, even in 2012, and certainly today, could be made that this is not technology in search of an application. This is not something that we're inventing just for the sake of inventing it and then trying to find places we can pigeonhole it. In most cases of artificial intelligence, what I say we, but I guess I should say people in general, are doing is responding to very clear needs for the sorts of product that artificial intelligence can provide. Now, any discussion of artificial intelligence, machine learning, etc., is going to have to look at some of the properties of this technology. I'm going to look a little bit about them here, and then in another module much later on in the course, we'll look at this in a lot more detail. But for now, let's look at 4 major machine learning types. And I'm using, so remember from the earlier presentation, right, we had artificial intelligence as a wide category, then machine learning as a subset of artificial intelligence, and then neural networks as a subtype of that. So, talking about machine learning, this is more learning that uses graphs and networks and neural networks in particular, and not so much artificial intelligence that is rule-based or expert system-based. And as we discussed before, there are various reasons why people aren't depending on those sorts of AI anymore. One of which is the great successes that neural network type approaches have been able to demonstrate in the last 10 years or so. So there are four major types of machine learning. Their technical terms are supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. But these could also be characterized as task-driven approaches, data-driven approaches, a hybrid of the first two kind of approaches, and then finally environment-driven approaches where we're getting some kind of feedback from the environment. So those are the overall approaches, but what does that break down into for practical applications? Well, modern analytics is based mostly on supervised machine learning and neural networks. And these in turn provide us with the following capacities. And this is a partial list. I don't think it's a full list, but it gives you a pretty good sense of the sorts of things we can do with these systems. Classification, regression, which is to say finding a trend or a line in a group of data, or in a group of data. I don't know what the plural of data is because data is a plural. Finding a pattern or line in data. How's that? Clustering, which isn't quite the same as classification. Feature extraction, which is a way of trying to understand the data without all the noise. Rule learning, and prediction. So different types of learning produce different types of these applications. Supervised, for example, will be used for classification and regression. Unsupervised is used for things like clustering and other applications. And then reinforcement learning can be used for things like, say, predictions. Classification. There are different approaches to classification. We can have binary classification, true, false, yes, no, qualified, unqualified, etc. We can also have multi-class classification where we're using more than two class labels. For example, nationalities would be a multiple class. Grades for a test grade might be a class. I got an email that just came in. Maybe you talk too much. It's from Protocol, and this is my third hour of presenting today, and it just gave me a moment of existential doubt. And then also multi-label classification. Things like tagging or hashtags is an example of this, where we have one entity and we apply different tags to it. So these are all ways of classifying that can be performed with artificial intelligence systems. Regression, as I mentioned before, is the idea of looking for lines in data. And you can see here in the table, in the illustration, it's different from classification in the sense that classification will divide your data set, whereas regression will just simply draw a line through your data set. There are different methods of regression. Simple and linear regression, which is what we see here. We might have nonlinear or polynomial regression, and something called lasso or lasso. I still don't know how that's pronounced anymore. least absolute shrinkage and selection operator, or ridge regression. So if you create a topography of your data rather than simple representation as you see in 2 dimensions here, then ridge would walk along the ridge of that topography. The other application is clustering. Here we're identifying and grouping data points in large data sets without concern for the specific outcome. What that means is we're not giving the AI a set of labels and asking it to sort things according to these labels. Rather, we're entrusting the AI to identify groups that we might not have considered in the data. So we're not going to tell it find, whether this is a grade 3 paper or a grade 4 paper. We're not going to tell it about grading at all. We just give it a bunch of papers and ask it to sort it into clusters. And then after the fact, we might ask, well, what do these clusters mean? There are different methods. You can partition your data, which is very similar to classifying, but you can partition it by features, by similarity. You can cluster by density. You can cluster it by the structure. You can classify it using grids, models, other constraints. There's a variety of approaches to clustering, a variety of algorithms. Feature extraction is a way of choosing a set of unique, relevant, or salient features that reduces the number of features in a data set and makes it more easily used by other applications. And this illustration we have here is a classic example of feature extraction. The feature that we've extracted are buildings or built-up areas, or maybe lawn. It really depends on how you've chosen to extract, right? And so we have a complex aerial photo of a neighborhood, and then we run feature extraction on it, and we have the building infrastructure and the trees and grass separated as 2 separate features. And that can tell us all kinds of interesting things just by looking at it. We can see half of the use of the land here is for, is covered with houses, cement, concrete, or whatever. Or it can be used as input to another process. There are different ways of talking about types of learning, and you'll see these discussed in discussions of artificial intelligence. One is rule learning, and that might be used to create or set up expert systems. And I said, expert systems are beyond the domain of this particular discussion, but they have their advantages in certain restricted circumstances, assuming you get the rules right. And this is a mechanism for getting the rules right. So you might use rule learning artificial intelligence to discover interesting relationships, and in particular, if-then statements. And as an aside, if you can extract if-then statements out of data, then you are able to construct a wide variety of representations, either rule-based representations or more complex representations that have rule-following sorts of properties. There's also reinforcement learning. In previous work, I've talked about this as learning through back propagation. And that's just one mechanism for reinforcement learning. Basically, it's to learn by trial and error in an interactive environment. So your AI tries something, the environment provides feedback, yes, no, or whatever, and then the AI adjusts all of its weights and measures and tries again. And it keeps going until it reaches a state where it's no longer getting negative reinforcement from the environment and getting only positive reinforcement. And then finally, deep learning is machine learning. In other words, it's learning with neural networks. But what makes this different is you have an input layer and you have an output layer, and then in between you have multiple layers of neurons. So you have a whole bunch of connections connecting each of these layers. And a way of characterizing deep learning is to say that all of these intervening input layers constitute a quote-unquote representation or a model. And so what you're doing with deep learning is you use the input, you use the output, and you run it through a bunch of iterations using data, and it builds this model for you. Now, it's not a model in the sense that it has principles, rules, laws of nature, whatever, but it is a model in the sense that you can talk about it as though this organization, this structure, this resulting neural network is a representation of whatever environment that we're talking about. Okay. There we go. So, in Module 2, taking all of this and breaking it down into actual applications. In other words, the actual things that we can do with these core capacities of regression, classification, clustering, etc. Now, I began with a classification offered by Gartner, which gives us the first four: descriptive, diagnostic, predictive, and prescriptive analytics. And I've added to that two more types of analytics: generative and deontic. And we can think of these as roughly corresponding to a question for each of them. For descriptive, what happened? Or maybe I could generalize that a bit more. What is the case? Or even to simplify it, what is? Diagnostic applies some kind of interpretation to that. I've rephrased the Gartner question. My rephrasing is, what kind of thing happened? So descriptive would tell us an email came in. Diagnostic analysis would tell us it was spam. So some kind of, say, clustering or categorization is happening. The third set, predictive analytics, asks what will happen. Now, we have to keep in mind, right, this is not going to be direct causal information, causal knowledge. So what we mean here is what will probably happen, or what is likely to happen, or all other things being equal, what is most likely to happen. But generally, its focus is on the future. The next type of analytics, prescriptive analytics, answers for Gartner and for me, how can we make it happen? And even to a degree, making it happen itself. And so it's moving into the recommendation sphere of things. So in learning, we might have learning recommendations, adaptive learning, hiring, pricing, etc. But there's more to making than just making something happen. There's actually making new things. And so I've added generative analytics to apply to the tools, the AI tools that are making new kinds of content, making chatbots, auto-generating animation, even all the way to the point of artificial teachers or interactive agents. And then finally, there's a class of analytics which goes beyond that, deontic analytics, which answers the question, what should happen? So let's consider these. So, as I said, in descriptive analytics, we're talking about description, detection, reporting, which includes aggregation, it includes filtering, it includes recombining information. descriptive analytics is going to use technologies like data lakes and data marts and all of that side of data management in order to produce, say, dashboards such as the one presented here on the slide. Diagnostics takes all of that information and, as I said, looks more deeply into it to detect patterns and trends. Categorization, classification, recognition tasks. There's a number of others. And so, for example, we have here a bunch of diagnostic processes. The information coming in, calls, data, output, reviews, all of that's fed into and analyzed to produce things like heat maps, run rate, text analysis, etc. There's a whole range. I don't need to provide more examples. We will look at dozens of examples as the week goes by. The predictive analytics really work in two stages. As I said, they're answering the question, what will probably happen? And what happens is, in the first stage, we take the historical data of whatever sort of phenomenon we're looking at, and we run it through machine learning algorithms, different algorithms for different sorts of predictions. And that produces for us a predictive model. In other words, one of these representations that I was talking about when I was talking about deep learning. Then we take that model and we apply new data to it. So now we're actually using it to make predictions. And the outcome of the new data plus the model provides us with the prediction. So it really is a complex way of saying what happened in the past will probably happen in the future. And that's true, and it's subject to all of the sorts of, room for error, skepticism, and doubt. But what's different about this is that it's taking massive quantities of historical data, much more than any individual human could take into account. And in some cases, it's taking that data as unlabeled or unfiltered, so that it's detecting patterns that we don't even have words for in the data, and using that to generate the model. And then these properties that we don't even have words for inform the prediction that it makes. Now, that makes it pretty hard to understand how the model is working, but it gives us much more sensitivity to different variables in our prediction, and ideally can make these predictions more accurate. Prescriptive analysis takes this and recommends solutions. So it's not making a prediction properly so called, but it's taking a model and then it applies different hypotheses or different possibilities to that model and makes predictions based on that, and then from that may select the optimal outcome based on a set of criteria. So, in marketing, for example, which is where this example comes from, it says, work on this deal, not on that one. Prioritizing the deal funnel, if you will. Sell this product, not that product. Do this task, not that task. Send this message, not that message, for marketing. And you're looking for benefits that, in this case, improve sales outcomes. Success rates, accuracy on forecasts, deployment of human resources, etc. Ultimately, for a company like this, it boils down to return on investment. But that might not be the case in all instances of learning. At least I would certainly hope not. Generative analytics takes data, often partial data, and creates new things. So it's kind of an extrapolation based on previous experience and some current data. And what's interesting about this is that you can give it very limited input and use a model to produce really interesting original or really interesting output. This diagram here, what we've done, or what they've done, is on the very right hand is the original that they've gotten the input from. Then on the very left hand, you see a partial image from that original. And then the 4 middle columns are extrapolations that generative analytical systems have made. In other words, given the input only and not the original, what did they think the original was? They're pretty close. Or they're interestingly different. Like the cat with the smile, the analytics knows there's a little piece of paper or something there, but it doesn't know what it is, so it makes something up. It picks something else out of its vast repertoire of paper type objects, or maybe underwear typed objects, I don't know. Systems like GPT-3 use this sort of analytics to generate original content, to write poems, to write death metal, to create images of people who don't exist. There's been a whole range of these come out over the last year or two. Deontic analytics looks at the expressions of sentiments, needs, desires, etc., in order to determine what sort of outcome would be best. So you can see how it's an extension of some of the other kinds of analytics. It's only the criteria that are used are criteria for optimizing an outcome is a criterion or criteria that are based on ethical or deontic generally considerations. What ought to happen, what should happen, what must happen. So we see on the right-hand side things like consumer expectations, social concerns, privacy risks, etc. That's the human impact, which is the deontic part, and we apply those to issues like complexity, trust, finance, management in order to come up with what should happen. Things like recommendations for education, for regulation, adaptation, or social policy. That's it. That's what we're covering for this module. What we're going to do over the next 2 days is look at the examples. I've amassed a ton of examples of the different types of analytics that I've talked about here, and we'll consider, first of all, are we missing types of analytics, or missing broad categories of applications of analytics, and can we find more examples of the applications that we already have? And then finally, is there a better way of thinking about this? And it's important, at this point to be clear that, the categorization of, descriptive, prescriptive, etc., although it's intended to be a principled categorization, that is to say, it's intended to be reflective of actual differences and the causal efficacy of different approaches to analytics, it's also at the same time something that can be seen as arbitrary and imposed over the data. The actual data that we're working with, I guess, are the actual links to descriptions of applications out there in the world, and then everything else is something that we're bringing to the equation. Now, I think that's an interesting thing that we're doing, bringing this other stuff to the equation, but we need not to lose sight of the fact of, we need not to lose sight of the distinction between what's out there and what we're bringing to the discussion. Because, it's kind of like we, as a course, are acting like artificial intelligence agents ourselves, right? And we're doing things like regression, classification, prediction, etc., ultimately to perform some sort of deontic analytics, what should happen, right? So all of the conditions and concerns that apply, which we'll talk about in the next module, but all of these concerns and considerations that apply to analytics also apply to us as a collection of people organizing, classifying, linking, etc., all of the resources that we're looking at and all of the discussions that we have. So that's what we're doing this week. That's what we're in the process of doing. I'm trying to follow the pattern of introducing gently into things, because that's how I have to approach these things, so that I can sort of gradually get myself into deeper and deeper water, so that if I begin drowning, I can get back pretty quickly. I'm not sure if that metaphor really works, but that's the one I have. So anyhow, that's what I've got for this presentation. I hope you found it interesting, and I'll be back tomorrow at noon in this precise spot with the beginnings of the discussions of the examples of the applications of learning analytics. Till then, I'm Stephen Downs. Have a good day.